So the last idea we're going to look at in this perms and coms is what's known as the Pigeonhole Principle. It's a pretty basic idea. If you've got n plus 1 or more objects, and you've got to place them in n holes, boxes, whatever you want to call them, then there must be at least one hole that contains more than one, so 2 or more objects, because you've got more objects than you have holes. So one of them's got to have more than one. That's the Pigeonhole Principle. So, alright, so let K be the maximum number of objects you can put into these n holes without having more than one object in a hole. I'm going to prove that K is less than n plus 1. And here's my proof. I'm going to do it by contradiction. And I'm going to assume that K is in fact bigger than or equal to n plus 1. So the opposite of what I'm trying to prove. Now, the maximum number of objects will equal n. Every hole has one object. So K therefore is less than or equal to n. But now straight away I've got my contradiction. It's as quick as that, because I've assumed that it's bigger than or equal to n plus 1, but then logic tells me it has to be less than or equal to n, so it can't be greater than or equal to n plus 1. Thus, it must be less than n plus 1. It's a bit of a proof. Do you need to know it? Probably not. Alright, let's generalise it. If K or more objects are placed into n holes, then at least one hole must contain, and there's the notation, K divided by n with the, you'll notice, brackets with the bottom bit missing. You might not have seen that notation before. That's what we call the ceiling function. So its symbol is, you've got the brackets but like with the bottom cut off. If that is equal to y, it basically means x has to be bigger than y minus 1 but less than or equal to y, somewhere in there. All it's really saying is you always round up. You always round up to the next whole number. Even if it's like 2.1, we would say, oh well, that's 3. You just round up. There's also another thing called the floor function which does the opposite, but that's not what we're interested in here. Alright, let's try and put it into some sort of context. And what on earth are we doing here? We've got this set of integers going from 3 to 12. We want to know the least number of integers needed to ensure that there will be a pair of numbers that add up to 15. So how many integers do I need to pull out there to guarantee that I've got 2 that add up to 15? You see, if I was to just pick 3 and 5, I can't guarantee I've got 2 integers that add up to 15. If I was to pick 3, 5 and 7, I still don't have 2 that add up. So what's the least number I need to pick to guarantee I can get a pair that adds up to 15? That's what this question's asking. What I do know out of all those numbers is that there are 5 possible pairs I could have. And there they are. I could have the 3 and the 12, the 4 and 11, the 5 and the 10, the 6 and the 9, or the 7 and the 8. As long as I've got one of those combinations there, I'm okay. So how many do I need to select? Well, n is equal to 5. What I basically created here are the pigeonholes. So what I could imagine is these are like little addresses, and I'm going to randomly pick a number and put it in the right address. And it's not until one of these addresses has 2 numbers in it that I'm okay. So the question now is, how many numbers do I need to pick to guarantee that one of these has 2 in it? Well, it must be 6. It must be 6. Because it is possible I could pick 5 and there still be 1 in each of them. But as soon as I pick that 6th one, I must have a pair. As soon as I've got one more than the whole. Now, using that notation, I could have solved it this way, because I want it to equal 2. So K, that's what I'm trying to find, how many objects do I need to get being placed into n holes. I said there were 5 different ones. So K over 5, and I want there to be 2 numbers. I want there to be a pair. So I'm saying this ceiling function must equal 2. Then by its definition we're saying, well, that means K on 5 must be in between 1 and 2. But I always round up, so the equal sign's on the 2. Multiply both sides by 5, and I now get that K must be in between 5 and 10. But it can't be 5. And I want the least number. Well, the smallest number that would do that would be 6. So that's how I could use that function to solve the problem. Again, logic could do it, or I could use the function to do it. We've got 50 points, we're just going to put 50 dots in a 7 by 7 square. What is the maximum distance apart that the two closest points that I put together could be? So I could randomly place these 50 points, but what's the biggest distance I could put the two closest ones? Right, so you get your head around what that's saying. I'm going to put them anywhere. Now once they're all down, I find the two closest ones. What's the maximum distance they could possibly be apart? That's what this is asking. So what I could do is I could say, well, this 7 by 7 square, conveniently, 7 by 7 is 49 and I'm putting 50 points. So I could divide it up into 49 1 by 1 squares. They become the holes. Those squares are where I'm going to place all these dots. Now, how many dots do I put in each square and so on? Now the Pigeonhole Principle tells us there are 50 points. So there must be a square in there that contains 2 points. It would be possible we put one in every single square, and that's going to maximise the distance apart there, but there must be one that's got 2. But inside that square then, that there's 2, what's the furthest apart I could put those 2 dots? And it would be along the diagonal of that square. So what is the length of a diagonal of a 1 by 1 square? Square root of 2. So that would be the maximum distance. So we've solved that problem using this Pigeonhole Principle idea. Prove that in a group of n people, there will always be at least 2 people with the same number of friends. It doesn't matter how big your group is. Let's say the group is 6. There's always going to be 2 people on this table that have the same number of friends in that group. There might be one who has 5 friends. There might be another one who has 3. But there will have to be 2 of them at least that have the same number of friends. Here's how I solve this one. It's not going to be possible for one person to have no friends and another person to have n-1 friends. Okay? Impossible. Again, let's go back to our 6 people here. You're telling us you have no friends. Oh, sorry about that. Whereas Mr. Popular here is saying, hey, I got 5 friends, so n-1. But hang on, that's not possible because you said you don't have any. So both can't be true. It's got to be one or the other. So that means there's only n-1 possibilities. I'm going to choose to leave off the one where someone's got no friends because that's not true. That can't be right. You know? So these are the possibilities. Someone's got 1 friend, someone's got 2 friends, someone's got 3, up to n-1. So there's n-1 different number of friends a person could have. But there's n people. So n-1 number of friends would be all the different pigeonholes. We could ask each person, how many friends do you have? And then we'll put that answer in one of those holes, and so on and so on. But I'm going to ask n people this question, and I've got n-1 holes. So I must get to a point where I'm going to get 2 people tell me the same number. So by that Pigeonhole Principle, there must be at least 2 people with the same number of friends. And if you don't believe me, watch this. Back to our table of 6 here. Hey, here's a question for you. Out of these 5, how many are your friends?
I'd say only 1 person.
Only 1?
Yeah.
Okay, alright. Same question. Out of these 5, how many are your friends?
5.
5? Everyone? Okay.
Only 2.
Oh, so you're changing yours to 2 now?
No.
Because you weren't counting them as your friend. Oh, how embarrassing. How many would you say? How many? 5. Oh, 2 people just said the same number. See? Has to be. There's no way you could have done that without 2 people saying the same number. Alright, 16 positive integers are going to be written on the board. At least how many numbers, when we write them up, 16, they just could be any number you like. Just 16 numbers. Got to write them on the board. At least how many numbers will leave the same remainder when divided by 5? Okay, totally random. But there are only 5 possible remainders if you count 0 as a remainder. There are 5 possible remainders. So what we're really saying is, These 16 numbers I could place into one of these 5 categories, one of these 5 pigeonholes. Whatever the remainder is, that's where we're going to put it. So we're placing 16 objects into 5 holes. This is where I'm going to use that ceiling function. So I want 16 divided by 5, which is 3.2, but we always round up, so there must be 4. Must be 4. And if you don't believe me, let's come up with 16 random numbers. Well, you've had a turn over here. Let's start over here. Give me a random, any positive number you like. 2. We have 2. 23. 12. Next table. 24. What was it? 76. And 19. Next table. 5. 47. 97. 31. Whoa, 738. Next table. 99. Okay, 4 to go. 64. 18. 80. And last number, 70. Okay, so we just claimed there must be at least 4 of these numbers that will have the same remainder when we divide by 5. What are the remainders? 2, 3, 2, 4, 1, 4, 0, 2, 97, 2, 31, 1, 738, 3, 99, 4, 64 is 4, 83, 0 and 0. So what did we say? There must be at least 4 that will have the same. So which number am I looking for? Remainder 2 is looking good. 1, 2, yeah, look, there we go. 1, 2, 3, 4. So there must be at least 4 that have the same remainder. Were there any others that had the... 4. Yeah, 4's got 4 of them as well. So there you go. Pigeonhole principle works for that one. Oh, this one's good. A computer is going to generate a random 3-letter word. Now, they're our maths words, so there could be nonsense words, that's fine. How many words need to be generated to ensure that there is a word that has been generated 8 times? It's just random words have been thrown out. We want the same word to come out 8 times. So the number of possible words. Okay, basic counting principle. First letter, 26 possibilities. Second letter, 26 possibilities. Third letter, 26 possibilities. There are 17,576 possibilities, or for the sake of our question, pigeonholes. Because when it gets spat out, we're going to put it against that word. Okay. We're trying to work out how many we need to make the answer 8. We want it to be generated 8 times. So therefore, the K on the 17,576 must be between 7 and 8, but we round up. Multiply out. We want, I guess, the minimum number to ensure. So it must be 1 more than the 123,032. We need to generate 123,033 words in order to guarantee there is a word that's been generated 8 times. Last one, last year's HSC. Sports Association manages 13 teams. It wants to check the age of the players to make sure no one's cheating. Anyone that has more than 3 players above the age limit is going to be penalised. They found that 41 players were above the age limit in this competition. Will any team be penalised? Will any team be penalised? Yeah, unfortunately you couldn't just say yes or no because they said justify your answer. Okay, and justify it correctly too, mind you. So 41 divided by 13, the ceiling function of that is 4. So yes, by the Pigeonhole Principle, this one will be above the age limit. They're going to be penalised. 14H.